Welcome. Today we'll be discussing section 4.3. Topics include product to sum identities, Fourier function, as well as sum to product identities. So to start with product to sum, we have three cases of cosine alpha times cosine of beta equals 1/2 times the quantity of cosine of alpha minus beta plus cosine of alpha plus beta. We can also have sine of alpha times sine of beta. And this one we'll see it be 1/2 times cosine of alpha minus beta minus cosine of alpha plus beta. And finally, we can have a combination of sine and cosine. So we write as sine of alpha times cosine of beta is equal to 1/2 times sine of alpha minus beta plus sine of alpha plus beta. Now, notice if we have cosine times sine, then we just can use the commutative property of multiplication to put it back into this format and follow the identity. Some things that may be easier to remember is that if you have cosine, if you have two different ones, then you're dealing with sine. Now, oftentimes what we'll use this for is if we have cosine squared or sine squared, we can then think of alpha and beta being equal, which then runs through the formula just as is. So what application is this useful for? And that is Fourier functions. So how we describe Fourier functions is a function f of x where we have a0 plus a1 times cosine of x plus a2 times cosine of 2x plus, and we'll continue this forward till we get to some integer n. I'm going to write capital N. And we have cosine of capital N x. So we have cosine, but we'll also add this same sort of mechanism with sine. So we'll have b1 times sine of x plus b2 times sine of 2x. And again, we'll add this all the way to b to the n of sine of nx. Now, some things to note is that a1, a0, all the way to an, b1, bn, they're all constants with that either an or bn is not 0. So we can think of this as if I had 0 x to the third plus x squared plus 4, I wouldn't call this a polynomial of degree 3. I would call this a polynomial of degree 2 because we would omit this 0x cubed. So similarly, we have to have at least one of these, bn or an, to be a non-zero number. Otherwise, we would reduce the order. So instead of degree, we're going to call this order n. So this would be an example of a Fourier function of order n. So let's have an example of a Fourier function, but we have to define it using the product of some identity. So example 1, let f of t be equal to 1 minus sine of 3t, and we're going to times this by sine squared of t. So this is one of those situations where we're going to take this sine squared and say that that is really sine t times sine of t, which we can use our product of some identity to get this equaling 1/2 times the quantity of cosine of t minus t minus cosine of t plus t. Now, t minus t is 0. Cosine of 0 is pi over 2. Oh, sorry, is 1. Cosine of 0 is 1. So what we can instead write this as 1, which then we can distribute the 1/2. We can write this t plus t, and so that's 2t. So we have 1/2 plus 1/2 cosine of 2t. Sorry, this is a minus. So we have 1/2 minus 1/2 cosine 2t. That is equal to sine times sine. Sine t times sine t. So we're going to substitute that into here now. And we get f of t equaling 1 minus sine of 3t. And we now have this being times by 1/2 minus 1/2 sine of 2t. Cosines. Cosine of 2t. So from here, we distribute and we get 1/2 minus 1/2 cosine of 2t. We distribute the negative sign 3t, and we get minus 1/2, or sorry, yeah, minus 1/2 sine of 3t plus 1/4 sine of 3t times cosine of 2t. We again have a product of sines and cosines. So we're going to use a product to sum rule. This time, we're going to use a third one. And we'll find that this quantity here of 1/4 sine of 3t times cosine of 2t, this is equivalent to, run through the formula, so this is 1/2. We get 1/2 times 1/2, so 1/4. And we have times quantity of sine of 3t minus 2t, which is just t. We're going to add sine of 3t plus 2t, which gives us 5t. Distribute the 1/4, and we get 1/4 sine of t plus 1/4 sine of 5t. Okay. So now I'm going to substitute this quantity in for this expression, or this term. And I'm also going to rearrange it to be in the form of the Fourier transform. So we're going to have ascending order. And what I mean by that is I'm going to have x, 2x, all the way up to the highest number times x, which in this case is 5. So when written out, we have f of t is equal to 1/2 minus 1/2 cosine of 2t. And now I'm going to have plus 1/4 sine of t minus 1/2 sine of 3t plus 1/4 sine of 5t. And this is my Fourier function. And I look at my highest value of cosine, it's 2. I look at my highest value of sine, it's a 5. And I know that this is a Fourier function of order 5. So now let's do product or sum to product. So with these identities, we have cosine of u plus cosine of v is equal to 2 times the quantity of cosine u plus v divided by 2 times cosine of u minus v divided by 2. We have cosine of u minus cosine of v equaling 2 times sine of u plus v all over 2 times cosine times sine of u minus v divided by 2. We'll also have sine of u plus sine of v, which yields 2 times sine of u plus v divided by 2 times cosine of u minus v divided by 2. And finally, we can have sine of u minus sine of v, which equals 2 times cosine of u plus v divided by 2 times sine of u plus v divided by 2, which this covers all instances of cosines and sines being converted into a product. So an example of this would be if I want to find all solutions to this following equation. Sine of 3x minus sine x equals 0. Now, we could also describe this question as I have a Fourier function and I want to find out when this Fourier function is equal to 0. So we look at our identity. We have a sine minus a sine. So we're going to use the fourth one. And so we can say that sine of 3x minus sine of x is equal to 2 times cosine of u plus v, so that's 4x divided by 2, so we have 2x, times sine of u minus v, which then that is 2x divided by 2, so we get x, and this is still equal to 0. So apologies, I wrote sine of u plus v. This is u minus v divided by 2. That's a similar pattern for all these. So now from here, what we can do is go, all right, I can divide by 2. So if I divide by 2 or times by half, that gets rid of that. If I times by 0 by half, doesn't matter, it's still 0. So essentially what I have here is I have cosine of 2x is equal to 0, or sine of x is equal to 0. So when I solve for, let's say, cosine of 2x, we get 2x equals plus or minus cosine inverse of 0 plus 2 pi n. Remember, n is an integer in this instance, and this gets us all possible values of x. Well, we want just x, so we're going to divide by 2, but we also want to find out what the cosine of 0 is, or inverse cosine of 0, which is pi over 2. So we have 2x is equal to plus or minus pi over 2 plus 2 pi n. Divide the entire equation by 2, and we get x is equal to plus or minus pi over 4 plus pi n. So these are two different solution sets. We can have the positive pi over 4 plus pi n or negative pi over 4 plus pi n. Now we have to find another solution set for sine. So we have x is equal to negative 1 to the power of k sine inverse of 0 plus k pi. Sine inverse of 0 is 0. So negative 1 to the power of k times sine inverse of 0 just goes away, which leaves us with x is equal to k pi. Again, k is an integer in this fashion, and we can make a note of that and just say where n and k are integers. And that would be a complete answer. So again, how this could be spoken in terms of Fourier function is the Fourier function of sine of 3x minus sine of x is 0 whenever x is equal to plus or minus pi over 4 plus pi n, or x is equal to k pi, where n and k are integers. Okay. So let's do another example. Example 3. We want to find all solutions to sine of 3x plus cosine of 5x. And that equals 0. So again, we want to find this Fourier function. We want to find where it's equal to 0. We'll look to sum to product, and we'll notice that we don't have a combination of sine plus or minus cosine or cosine plus or minus sine. Well, that's because we would be redundant because we can transform one into the other. So remember that we have the identity that sine of any theta is equal to cosine of pi over 2 minus theta. We can apply that here, substituting 5x in for theta, and we get sine of 3x plus sine of pi over 2 minus 5x is equal to 0. Now we can use the third identity for the sum to product, and we get 2 times sine of u plus v divided by 2. So we'll write it out this time, 3x plus pi over 2 minus 5x all over 2. We'll have sine of, cosine of u minus v divided by 2. So we'll have 3x minus pi over 2 minus 5x all over 2. That still equals 0. So note that this minus is to the quantity of the entirety of the inside function. So this negative will distribute. So let's simplify, and we have 2 times sine of 3x minus 5x is negative 2x. When we divide by 2, we're left with pi over 2 minus x. And then, pi over 4 minus x. And then we'll have cosine. And when we distribute, we're going to have positive 5x plus 3x. So that's 8x divided by 2. So that's 4x. And we're going to have a negative pi over 2 divided by 2. So negative pi over 4. And again, this will all equal 0. So now we will apply the exact same way of trying to find the solution. And that is, we will write down cosine of 4x minus pi over 4 is equal to 0. And when we try to solve this, we take the cosine inverse, and we'll have so we'll have 4x minus pi over 4 is equal to plus or minus cosine inverse of 0 plus 2 pi n. Solving for this equation, we get this to be pi over 2. So we'll have 4x minus pi over 4 is equal to plus or minus pi over 2 plus 2 pi n. We'll then add pi over 4, divide by 4, and we have x is equal to plus or minus pi over 8 plus pi over 16 plus pi 1/2 pi times n. So then that covers just the cosine. And now we want to do the sine, which I'll squeeze it in over here. And we'll have sine of pi minus 4 minus x is equal to 0. Take sine inverse, and we'll have x, or pi over 4 minus x is equal to, we'll have -1 to the k, and this will be times sine of 0, which is 0, so that'll cancel out, leaving us with k pi. We then subtract pi over 4, divide by -1, and so we'll get x is equal to pi over 4 minus k pi. And we have obtained our solution sets. Now, these examples, you might try to work it out, and you might flip these, or you might change this sign to a cosine, or there's many different ways they can try this, and when you go through it, you might get a different answer. So I hesitated earlier because I deviated from my notes, and we would eventually get to the same answer because of this n and this k. They are able to kind of hide a lot of different versions in themselves. What do I mean by this? Well, here I have k equals pi over 4 minus k pi. Well, if I make k be negative, and so let's define q, where q is -k, I then have x is equal to pi over 4 plus q pi, which now looks different, where q is an integer, but it's just the negative version of k swallowing up this minus sign. And we can do the same thing when it comes to over here with this plus 1/2 pi over n. I could define m as -n, and now I have a minus 1/2 pi n. And so it's good to be wary of the multiple different ways that you could get a solution. Okay, so going on to example 4, we'll have it be prove an identity. Now, with these, it'll follow the same exact path as most proving the identities. meaning we want to take one side, the quote unquote uglier side, and find a solution by breaking it down. So, for example 4, let's start with sine of 5x plus sine of 3x divided by cosine of 5x plus cosine of 3x is equal to tangent of 4x. This is what we want to verify. We want to see, is this true? So what I mean by uglier side is basically the side that has fractions and a bunch of stuff, and we want to try and get this into a simpler form. So we start off on the left-hand side, and we can start picking apart these two equations. And so let's just start off with sine. We have sine of 5x plus sine of 3x. And what we want to do is first just use the sum to product identity. And we'll have this be equal to 2 times sine of 5x plus 3x, which is 8x divided by 2, and we get 4x, times cosine of 5x minus 3x divided by 2. So that is 2x divided by 2. So we just get sine of x, or cosine of x. And now when I take a look at the bottom, I have cosine of 5x plus cosine of 3x is equal to, and we'll have 2 times cosine of the same value, 4x, times cosine of the same value as above, x. Well, all that we really have to do now is divide these two solutions. Well, 2 cancels with 2, cosine x cancels with cosine x. That leaves us with sine of 4x divided by cosine of 4x, and we have tangent of 4x. Therefore, we have verified the identity. We got there. And we could try and see the roadmap to start off with this. When you see a tangent, think of it as sine divided by cosine. And when I have that, I instantly saw that I had 2 sine of 4x times cosine of x. So I imagine that I'm probably going to get this 2 to cancel. I'm probably going to get this cosine to cancel. How can I get those to cancel? Well, let's just take a look at the bottom. And when we applied one identity, we got to this stage and it canceled and we were able to solve it. Sometimes we might have to do an additional step. Maybe there's a Pythagorean identity that we have to use, or another add pi formula or something like that, to make it be visible on where we want to go. But just keep in mind of your target. You want to try and get to that section of the board. Because otherwise, if you apply the wrong identity, you can start spinning yourself in circles pretty quick with the endless trig identities that exist. So for your check on learning, I want you to write down the product to sum identity. Write down these 3. If you wish, you can also write down the sum to product identities, but as far as for credit for a class submission, I will only require the product to sum identity. Thank you for watching, and have a great day.